So in late 1800s, a German mathematician, Weierstrass, he was sitting on his couch sipping coffee, and all of a sudden he was like, how about I write the most important theorem of modern analysis? And he wrote the Weierstrass Approximation Theorem. So the Weierstrass Approximation Theorem states that polynomials can approximate continuous functions in a uniform way, in the soup norm sense. Basically, like roughly speaking, this means that if you draw any continuous function on a compact interval, then you can approximate it. You can draw a polynomial that hugs the curve of the function. So this theorem was later generalized by Stone, who like generalized it to a general compact Hausdorff space. But we're not gonna focus on this on that for this video. So in this video, we're gonna discuss like some applications of the Weierstrass Approximation Theorem, and then we're gonna talk a little bit about or sketch quickly the proof of this theorem. So let's first look at this application. So the Weierstrass Approximation Theorem, what it says is that if you look at the space of continuous functions on 0, 1, then the space of polynomials is dense in this space. If you have a function that has 0 moments for every power of x, so then the function must have been identically 0. So the proof of this thing, it's not that hard. So let me go ahead and show it to you, I guess. You could, for example, you could take a sequence of polynomials, let's say Pm, and then assume that this sequence converges uniformly to f, and you can do that by the Weierstrass Approximation Theorem. And then what you can observe is that if you integrate f of x against Pm, then what happens is that this thing, if you take a limit of it as m tends to infinity, this thing is gonna go to the integral from 0 to 1 of f squared of x dx. But on the other hand, this thing is 0, because each of these things is 0 using this fact. So because the integral is a linear operator, you can split it and you can see that each of these terms appearing here is going to be 0, and hence the whole integral is 0, and hence this is a limit of 0, and hence it's 0. So now we've shown that the L2 norm of the function is 0. But since this thing and the function is continuous, this automatically implies that f must have been identically 0. And by the way, we could interchange the limit and the integral here because of the uniform convergence. That's a basic analysis fact, I guess. So let us see some more applications. So this is the first cool application of the Weierstrass Approximation Theorem. Let's see some more. So here's a version of the Riemann-Lebesgue lemma, and what it says is that like if you look at usually an integral like measures the signed area, right, of a function. If you introduce some oscillations in the function in the integrand, then the oscillation, quote unquote, kills the area. So this is the idea of this fact. And like if I mean you could basically prove this in other ways, but it's nice to see that it could be proven by the Weierstrass Approximation Theorem. And let me show you the motivation, I guess, of the proof without getting too much into details. So since this thing can be approximated uniformly by polynomials, and since the integral is a linear operator, it suffices to observe the following. So let's observe what happens. Let's see what happens to this thing. So let's integrate from a to b, t to the k sine of xt. And let's see what happens to this as x goes to infinity. And then I'm going to show you how this thing automatically follows. So if you integrate by parts and upper bound this, here's what you get. So if you integrate by parts, take u to be t to the k, dv to be sine x t dt. And if you upper bound the trigonometric functions by 1, you have something like a to the k plus b to the k over x. And then there's the term coming from the integral, which is t to the k minus 1 dt after you integrate by parts. And if you evaluate what this thing is, this is going to be something like 2 times b to the k over x, something like that. The bottom line here is that if you look at this function for a fixed k, if you look at this function, it's gonna go to 0 as x goes to infinity. And this is basically it. This is all you need to prove the result, because as I mentioned, you can always find a polynomial that approximates f in the uniform norm, let's say less than epsilon over 2, and then you observe that if you look at the integral from a to b of f of t sine xt dt minus the integral of p sine of x xt dt, excuse me, this is t. If you look at the difference of these things, you can upper bound it easily by b minus a, let's put it this way, b minus a times the norm of f minus p, which is bounded by, let's say, epsilon. So you could do something like here, b minus a, for instance. In other words, you could upper bound the difference between this thing and this thing. Let me clean this up a little bit. So you could upper bound the difference between f of t, this integral, and that integral, which means it suffices to show that this is very small when x gets, when x goes to infinity, to get the result, because this is already very small, right? The difference between these is already very small. So once we've shown that this is very small as x goes to infinity, or goes to 0 as x goes to infinity, we get this automatically. But we did because this thing implies that the integral of the polynomial goes to 0, because the polynomial could be written as ak t to the k from k equals 0 to some n, for instance, or m. And then you can use linearity of the integral to write it as a sum of terms like this, but each of the terms goes to 0, so this whole integral goes to 0 as x goes to infinity. So this is like a messy, quick sketch of the proof, but it's really a basic fact. There is really nothing here that is very deep. Okay, so let's move on to the next application. So for the next application, this one I really like. So it's basically saying that every continuous function could be written as like a series in polynomials. Let's go ahead and prove this, I guess. That's not hard. It's basically again, a direct, an immediate application of the Weierstrass Approximation Theorem. Here's what you can do. So you could find like some polynomials. We know by the Weierstrass Approximation Theorem that f could be approximated by some polynomials qn, like say with some constant with epsilon taken to be 2 to the minus n. Okay, so we know that we could find a polynomial q approximating f with an error epsilon, and hence we can find polynomials qn approximating f with errors 2 to the minus n. Okay, and then here's what we do: take Pn to be Qn plus 1, or Qn minus Qn minus 1, and take, for example, P0 to be Q0. Taking this sequence, you get what you want. Excuse me, let's use 1 here, since we're starting the series at 1. It doesn't matter, it's just an indexing thing. So, for this one, you will see that if you sum pn's, say from n equals 1 to m, this will be qm, okay? Because the sum telescopes, and we know that this thing converges uniformly to f, because this is how we constructed them, and hence we have this thing. We have this this result. The series is gonna be f. So this is again a very cool application of the Weierstrass approximation theorem. Before we go ahead and prove the theorem or sketch the proof of it, I'd like to make two notes that the assumptions made in the theorem. So if you look at the theorem again, the statement, you will notice that we're assuming compactness of the domain, and that cannot be. We cannot get rid of this assumption. This is very important. So let me show you some counter examples. So let's see some counter examples. For example, this is not an application. This is really an observation, I guess. If you look at a function like 1 over b minus x, this function is not bounded on AB, and if you define it on AB, you don't require compactness. You can't use the approximation theorem, and the reason is if say we assumed blindly that we can. Suppose the theorem applies. Well, then we know that there's a sequence of polynomials Pn such that if we look at the infinity norm or the sup norm of f minus Pn, we know that this goes to 0 as n tends to infinity. So we can choose n, or let's say for n big or huge, the sup norm could be made less than 1, which means we're gonna have something like 1 over b minus x is bounded by Pn, the sup norm, plus 1, for instance. So this is for large n. But this is impossible because this thing, when I speak of the sup norm, I mean a sup over AB, by the way. This is impossible because this is unbounded on AB, but this is bounded on AB. So this is a contradiction. So we cannot apply the theorem in this case. So this is an easy way to see this. Similarly, we cannot remove the assumption of compactness. We cannot, for example, take f to be defined on the whole real numbers and still apply the theorem. That doesn't work. For example, if you take the function, the exponential function, this cannot be uniformly approximated. And again, this is the same reason. So let me quickly show you. So suppose you have a polynomial p. So for a polynomial of degree n, say, then what we have is that p of x could be bounded by something like, let's say, some constant c times x to the n, because x to the n is the dominating term. So for large x. okay? So and then we're done, because you can observe that e to the x could be made bigger than this thing for large x. Once you observe this, and this is, of course, this is because e to the x over x to the n goes to infinity. Once you observe this, you can see that we cannot approximate e to the x by that. We cannot approximate e to the x by p of x. That doesn't work. So let me show you. So this is going to be bigger than or equal e to the x minus p of x by triangular inequality, which is bigger than, so let's make this strict. So this is bigger than cx to the n plus 1 minus cx to the n, which is equal to 1. So we have a strict inequality here. So if the theorem were true, then we must have been able to approximate e of x by p. Say we must have been able to make it less than 1. However, we've shown that for every polynomial p, we can choose x big enough to violate this inequality. This can't happen. So we can, however, approximate e of x by a sequence of polynomials converging to it uniformly. However, we cannot find a fixed polynomial that approximates it uniformly on like on the whole real numbers. That doesn't work. Okay. The compactness assumption is very important and cannot be waived, I guess. So I'm gonna wrap up this video by proving the Weierstrass Approximation Theorem, and I don't want to spend a lot of time on the proof because it's again elementary. But let me, I guess, show you the motivation of the proof, and that's gonna be enough. So the idea is that the exponential function could be approximated uniformly by a polynomial on a compact interval, and hence what we can do is we can introduce some exponential smoothing to f and look at this quantity over here, and the idea here is that this kernel, or this Gaussian kernel, it looks like this, something like this, and as we decrease h, when we send h to 0, the bump gets like steeper and steeper. It gets steeper and steeper. It's probably not the best figure, but the idea is that the area over here gets smaller and smaller as h goes to 0, and hence what we expect is that this is gonna converge to f of x as h goes to 0. The important thing is that because of the exponential smoothing we have, the convergence will not just be like pointwise, it's going to be a uniform convergence as h goes to 0. And that's going to be enough, because if we can bound sh, so if we can bound this difference by epsilon over 2, maybe let's use our function g now, just not to confuse things. So suppose we have a function g on AB, and we'd like to prove the Weierstrass Approximation Theorem. It's continuous there. Then what we can show is that the difference between shg and g can be bounded by epsilon over 2 in the sup norm over AB. And similarly, we can show that shg minus, there's a polynomial coming from the fact that the exponential function could be approximated uniformly by a polynomial. So there's a polynomial that approximates this thing uniformly by epsilon over 2, and hence we can approximate g by p with an error epsilon uniformly. So this is the idea of the proof. However, to prove this to prove this like rigorously, you just need to make like some observations real quick. And the main thing you need, as I mentioned, is the fact that we have a uniform convergence here, assuming f is bounded. So assuming f is bounded and uniformly continuous. So if we assume these two, then we can prove this fact, and the proof is not that bad. It's pretty elementary, or pretty standard. Let's put it this way. So maybe let me quickly justify it for you. Well, first of all, let me mention that. Let me remind you that if you integrate this function, this is square root of pi, and if you integrate this kernel that we're using here, u minus x over h du, this is going to be exactly h square root of pi. So this normalization makes the kernel a probability kernel. And the idea behind the proof is the following. Let me quickly just write the idea. So if you look at the difference of these two quantities, you can rewrite it because of this exponential smoothing, and because of this fact, you can rewrite it, or you can bound this as 1 over h square root of pi times the integral of f of u minus f of x times the kernel to the minus u minus x over h squared d cube. And after that, the idea is that if you look at this this function or this integral, you can split it into two integrals. So let's put it this way: the integral over u close to x plus the integral over u far from x. So roughly speaking. So after you do that, you observe that when u is close to x, this thing could be bounded by epsilon by continuity, and hence you control the first piece, and the second piece could be bounded because f is bounded and because of the exponential smoothing. So for the second piece, you could also bound it by epsilon, and hence the whole thing is or epsilon times this thing, and hence the whole thing could be bounded by epsilon. So the overall idea here is that once you do this kind of splitting thing, which is a standard thing in analysis, you can get a uniform bound on this in terms of epsilon. And this is gonna prove the uniform convergence. And once you have this uniform convergence, as I mentioned, proving the uniform convergence here is immediate by the fact that we have a sequence of polynomials converging uniformly to the exponential function. That was it. Thanks for watching.